All right, our air resistance problem, just to review. So we always want to draw the forces on the ball before it reaches terminal speed, it says. Always we draw an air resistance. And since we haven't reached terminal speed yet, that means the weight force is a little bit bigger. I'll write it as Fg because a lot of times the AP tends to do that. Now, the magnitude of the acceleration, does it increase, decrease, or remain the same as it approaches terminal speed? Let's be clear. The acceleration magnitude, meaning the absolute value, magnitude just means size. The magnitude decreases as the ball approaches terminal speed because the forces eventually balance. So the acceleration goes to 0. No, and they say set up but do not solve. That means Fg minus F air equals ma. And what we're going to do here is we're going to say mg minus the bv squared that's given is m. And now we're going to swap this out with the calculus notation we talked about before, okay, which is dv slash dt. For our purposes right now, this little dv dt, it's called a derivative. And just for now, for the next couple weeks, this is simply the calculus way of writing acceleration. We're going to define it more clearly later. But this is the step that we want to take. We want to rewrite it using this little fraction here. Okay? It does mean the change in speed with respect to the change in velocity with respect to time, but deployed in a special way that you need some more mathematical tools to work with. Now, when we reach terminal speed, the acceleration equals 0. And that means mg minus bv squared equals m times 0. That tells us that mg minus bv terminal equals 0. When we isolate v terminal, that's going to be, bv terminal squared. That means v terminal is going to be mg over b, all under a square root. Now, the energy dissipated by drag force. So we start off with all potential energy, and it becomes kinetic plus the dissipated energy that we lose due to air resistance, lost to air resistance. Now, you're not going to be tested on this, but it's a good question to ask. So we have all mgh, and it gets converted into 1/2 m, and our kinetic energy near the bottom is v terminal speed squared plus whatever was lost due to dissipated energy that I'll call ED. So this is going to be mgh minus 1/2 m, and I'm going to use this v terminal here. So v terminal is square root of mg over b. So when I square that, that's going to be mg over b, because it's square root of mg over b. We square the square root, we get the original function back. So this means our dissipated energy is going to be mgh minus 1/2 m squared g over b. All right, so that's your first taste of an AP problem with air resistance, like I said. I would hold you accountable for doing something like A, B, C, and D. You would not do question E.